about that now. Yeah. Okay, so we've completed the square. We're going to come back over here. We're going to rewrite the integral. 1 over, and this is going to be x plus 1 squared plus 16 dx. And if you look in your notes from last class, at the very beginning when we were talking about formula 17, I gave you an example similar to this, where if you kind of like imagine, you have to see here that this is a linear expression. So you could do like a basic u substitution right now, that u is this, and then this would really turn into like 1 over u squared plus 16, and then you could use formula 17. So we did that last class, so I'm not going to run through that all again. Yes? No? You sure?
Yeah.
Did you say that because what I said?
Yeah.
Okay, well, what do you want? Do you want me to run through it?
Well, I wanted to know, what if the denominator is squared? Because I tried doing numbers.
What if the denominator is squared?
Yeah.
Oh, the whole thing is squared. What if the whole thing is squared?
Well, just the denominator, like just the quadratic. And the
Yeah. If you would have had this, is that what you're saying? No, squared, sorry, squared. Is that what you're saying?
Yes.
Did you run across that?
Yes, number 30.
Out of our book or out of
From that sheet.
from that sheet?
I tried
Okay,
to do it.
so the way we could do this is to do this. Yeah, do this to the 4th power. And then complete the square here, and then do a basic u substitution, and then do trigonometric substitution. So like this would turn into, what would this turn into? This would turn into the square root of x plus 1 squared plus 16, right? All of that to the 4th power, dx. Now, yes, because we complete the square, right? And now just make a basic u sub here. What would your u sub be? X plus 1. And the nice thing is du is dx, right? And now if you rewrite the problem, we have integral 1 over square root of u squared plus 16 du. And now trig sub, right? Because I see the square root of something squared, so it's like x squared plus a squared. By the way, what is the trig sub here? Trig sub. U would be, we'll use u instead of x, right? Because it's u here. It would be a, and then what is it? Tan, right? Tangent theta. Makes it. Oh, yeah, I forgot to the 4th, sorry. To the 4th.
That's what makes it harder.
Yeah, is that, should I just keep going or? No, this is a different problem though. This is not the one they gave you, right? This is not the one they gave you. But this is the way it would go. Does that answer your question enough?
Yeah, I think so. I don't know where I went wrong with it.
Okay.
With the problem.
I'm happy to look at that problem, but let's just get through what we need to get to, all right, today. All right, so for right here, let's go back to this. At this point right here, I'm just going to use formula 17, all right? With the little u substitution that I'm not even going to show. I'm doing this substitution right here, right? That substitution. And formula 17. So this would be, formula 17 is 1 over a, right? So a for us is 4. Inverse tangent of u over a, but in this case, u for us would be that linear expression. So x plus 1 over 4 plus c. Is that all right? That's it. All right, so recap. If we have a constant over a quadratic, and that quadratic cannot be factored, then we will complete the square. Once we complete the square, we'll be looking at something like this. In this case, it's formula 17 because there's a plus there, right? So I do formula 17. Had this been a minus, then I'd use formula 20, right? Okay, so Do y'all see how this is like builds on itself very quickly, right? Like these things just really start to pile on top of each other. All right. So what have we done in totality today? Constant over quadratic. If the quadratic's missing the x, we've got 3 different formulas, right? And now constant over quadratic, if it's not factorable, we have completing the square, and then we go to the other formulas again. Okay. Remember, all of this is because we're going to have problems that we get to these things, right? And so we're going to like, oh, we finally get to that. Constant over quadratic, it's irreducible. Yes, thumbs up, I know how to do that, right? All right, how about this? Linear. Now the problem I'm about to show you, I want you to put a star next to this. This is probably one of the most highly debated problems that I do in this class, because the way that I teach it is not the way that it's shown in most textbooks, and it's not like if you go get help, tutoring lab or something, I would be willing to bet a lot of money they're not going to do it the way I'm about to show you, unless they took me for Caltech. If you go on YouTube or something and watch a video, I'm pretty sure it's not going to be what you're about to see, all right? But I believe that what I'm going to show you here is better for you mentally, like in terms of your evolution of thinking, all right? I think that what I'm going to show you is nice, all right? Okay. So what do we have? We have a linear expression over a quadratic, right? A linear expression over a quadratic. And that quadratic on the bottom is irreducible. You just have to take my word for now. If you try and factor the bottom, it's not going to factor, all right? Do we need to check it, or no? Okay, you believe me? How would we check it? So multiply this number times this number, you get 12. And then you take the number in the middle, -4, and you try and come up with 2 numbers that multiply to be this and add to be this. Well, 2 and 6, right? But you can't get the signs right, because it would have to be 2 times 6, right? 2 times 6. This is a little method that if you've seen it, cool. If you haven't, don't worry about it. I'm trying to find 2 numbers that multiply to be this, add up to be this. So I tried 2 and 6. Yes, those multiply to be 12, but they add to be 8. So then you say, okay, make this 6 here negative, but now it doesn't multiply to be 12. It's -12, right? So there's no way you're going to be able to get any 2 numbers that like fit perfectly or work perfectly. So it's not factorable. And it's not a constant, right? If this was just 1, what would we do? If that was just a 1 on top, what would we do? Complete the square, right? What we just did in the previous problem. But see, it's a linear expression on top. So how do we handle this? Well, think about it this way. This is at least the way when I was first thinking of how I could do this problem. Think about this. This is a big point. The denominator is quadratic, right? Okay. If you take the derivative of something that's quadratic, what do you get? Something that's linear, right? Like the derivative of a quadratic expression should be a linear expression. And my numerator is linear, isn't it? So I wonder if I just let u be the whole denominator, if the derivative of that is the top. Do you think it is? Let's see. If I let u be equal to 4x squared minus 4x plus 3, the whole denominator, the derivative of that is what? 8x minus 4, all of that, right, dx. Is that what my numerator is? No? Okay, I could factor a 4 out, right? If I pull a 4 here, though, but is that going to be that? Even if I pull a 4, if I pull a 4, it's going to be 2x minus 1, right? And this is what? X minus 1, right? So you all see, wouldn't it be awesome if this was 8x minus 4 up here? Wouldn't it? Because if this was 8x minus 4, then I would have du, wouldn't it? Wouldn't I? And it would just be just a basic u sub, wouldn't it? So what I'm going to do, this is the key, this is the part that, again, your tutor's not going to tell you to do it this way. What I'm going to do is I'm going to look at this, and I'm going to say, I really wish I had that up top. I really wish I did. And so I'm going to make it happen. I'm going to make this appear up there, right? So watch how I do it. I'm going to start with the x. I need an 8x, right? How many x's do I have here? Just one. I need 8. Can I just put an 8 there? No, right? But what I can do is multiply the outside by 8 over 8, couldn't I? That's 1. That doesn't change the problem. And then what I can do is I can take that 8 and I can pass it through the top. Is that fair? Is that legal? Is what I'm doing legal here? Yes? Okay, so now what I'll have is on the outside I have 1/8 because I took the numerator, the 8 on the numerator, and pushed it in. I've got 8x minus 8. Right? That good? Understand? Any questions? Now, does it match? Not quite. Not quite. Well, I'm going to do something to force it to match. I'm going to do the same thing I did when I was completing the square. I'm going to see that there's a hidden 0 here. All right? And here's my hidden 0. 1/8 integral 8x. What did I want? I wanted what? Minus 4? Okay. Let it be. Minus 4 plus 4. Isn't that 0? Okay, so I've taken away 4 and added 4. Okay, what was still there, though? I hadn't dealt with this. Minus 8? Does anyone disagree with that? That's the same problem? Now that is equal to 1/8 integral 8x minus 4. So I'm just looking at, I'm putting these two together like that. And then these two, let's put those together. What's that, minus 4? And then over 4x squared minus 4x plus 3 dx. Now this top is not exactly this, right? It's not exactly. It's pretty damn close, but it's not exactly, right? So now what I'm going to do is this. Any guesses? I'm going to break it into two integrals. It's going to be this integral. Am I allowed to do that algebraically? Can I split fractions like that? Yes. It's that plus 1/8 integral. Okay, what's in this, the top of this other integral over here? Negative 4 over 4x squared minus 4x plus 3 dx. Yes?
So I know we're not completing this part, but how come we did -4 and then +4 instead of +4 and then -4?
Because of what I wanted, right? I wanted -4, right? So I put a -4 +4. Good question. I'm glad you mentioned that. I did -4 +4 because I wanted a -4. So I put the -4 first so I could put it together here with this 8x.
So it was a plus 4.
If it was a +4, I would do +4 -4. Yep. The whole idea is to try and manipulate the numerator to make it look like to make it look like that derivative. And you should always be able to do this, right? If you have a linear on top and a quadratic on the bottom, when you take the derivative of the quadratic, you'll always have a linear expression, and you'll always be able to manipulate that top to make it look like that, right? You'll always be able to, whatever number's here, you'll always be able to put that on the outside, pass it through, and then you'll always be able to put a hidden 0 in there, and then split the two apart. All right, let's look at these integrals. What do you think of this integral? This is really nice, right? This is really nice, because I can just do a basic u sub, right? I mean, the whole motivation of doing that was this, right? If I do a u sub, if I do this u sub right here into this first integral, this integral becomes 1/8 integral. Okay, what is all of that? That's du, and so this is 1 over u. The bottom is u, right? du. What's the antiderivative of 1 over u? Natural log, right? So this is just super simple now for us, right? This is super simple. This one, on the other hand, is not. Because what do I have here? Constant over irreducible quadratic. How do we do that? eventually number 17. Well, it might be 20 or 19. It depends, but we'll have to complete the square, right? So this problem now becomes what we just did in the previous problem. All right? Constant over irreducible quadratic. So I'm not done. I've got more work to do. So I made my life nice here, but I still have work to do. Got it? Okay, so I'm going to come here. Let's see. Let's finish this off right here. Let's finish this one off. This would be 1/8 natural log of what? U, but what's U? 4x squared minus 4x plus 3, right? So that becomes that becomes that. Now I still have plus this integral, right? Plus this. And that answer, whatever it is going to go right here. Let's go do that over there. All right, I'm going to do some separate work. I'm treating it almost like it's its own problem. So this integral is 1/8 integral -4 over 4x squared minus 4x plus 3 dx. All right. So to handle this, how about we do this? How about we first make this -1/2 integral 1 over. Let's just pull that -4 out. That step's not necessary, but why not? -4 comes out, reduces, right? And now complete the square. Got to complete the square. So I've got to do some scratch work over here, right? I'm in the middle of scratch work, right? I'm in the middle of scratch work, and I'm going to go do scratch work for the scratch work. So I can come back here and put my answer in, all right? There's a lot of shit you got to keep in order here, right? I'm completing the square. All right, what's the first condition we have to satisfy for completing the square? Coefficient of 1 on the x squared term, right? So I'm going to factor a 4 out. 4 comes out. I've got x squared minus x plus 3/4. Okay, now I take the number that's sitting in front of x, -1, and I take half of it. And when I take half of it, I get just -1/2, okay? And now I square that number, and you get positive 1/4, and that's the number that I'm going to add and subtract. And that one I do have to do add and subtract. All right, so I've got here, this is equal to, let's see, 4 parenthesis, here's x squared minus, I don't need the 1x, I'll just put minus x. Here comes the hidden 0, plus 1/4 minus 1/4, plus 1/4 minus 1/4, right? And then I still had plus 3/4 there. When you do this, if you do it right, you're guaranteed that the first 3 terms are going to factor to be x minus 1/2, that quantity squared. So I'll have 4 parenthesis, then another parenthesis, x minus 1/2 squared. That takes care of those first 3 terms right here. And then you put those two together. -1/4 plus 3/4 is 2/4, which is 1/2. So you have 1/2 here. Close the parentheses. And you know what? Knowing where we're going with this, I'm going to leave the 4 on the outside. I'm just going to leave the 4 here, and I'm ready to go back to this integral. Any questions? I know some of you are following because I can hear you as you're responding to me. And I'm looking at other people, and some other people are just like, just like that. Yeah, thank you. It's just like this glare stare. So I don't know what that means. You have to let me know, or, you got to ask questions. You got to stop me, right? Okay, integral. Oh, you know what? Yeah, I'll do it. Integral 1 over 4 parenthesis, then another parenthesis, x minus a half squared plus a half, close parenthesis, dx. And that 4 on the outside, I can pull that out of the integral completely, can't I? It'll become a negative 1/8. I'm running out of room. Okay, negative 1/8 integral. This is going to go away. Is that all right? Negative 1/8, okay. 1 over x minus a half squared plus a half dx. What now?
Tangent, or
It'll be like a little basic U sub, and I'm going to wind up using formula 17. Right? Formula 17, because what I have is 1 over my variable squared. See, this is linear. This is a little linear expression. So if I do a little U sub, everything's going to be nice. U squared plus A squared. That's A squared. So A is actually the square root of that, isn't it? Okay, so I'm ready for formula 17 right away here. So equals by formula 17. I'm using 17 because there's a plus, right? Had this been a minus, I would have used formula 20. Okay, don't forget we have a negative 1/8 out front. Okay, here comes formula 17. Formula 17 says I do 1 over A. What's A? Is the square root of 1/2, which is the same as 1 over root 2, isn't it? You can do the square root top and bottom separately. So it's 1 over A, but A is 1 over root 2. That's going to wind up flipping, but I'll do that in a second. Inverse tangent of U, what's U for us? X minus a half over A, which is 1 over root 2. And then plus C, right? I'm going to have a plus C here. But remember, we're in the middle of this problem, right? Aren't we? We're in the middle of this problem, so we're going to bring that answer back. But we're there. We're there. We're done. Okay? We just got to put this all together. So this, all I'm going to do is just reciprocate this and put the root 2 up here on top of this 8 and put a negative in front. And then that inside, I'm not even going to touch it. I'm just going to leave it alone. All right? So over here, we have plus, right? Plus, but it turned out to be negative, didn't it? So minus the root 2 over 8 inverse tangent of x minus a half over 1 over root 2 plus c. There we go. We are having to work harder and harder and harder to do this, aren't we? There's more and more stuff we have to do to find these antiderivatives.
Is it okay if we use the square root in the denominator like that, or do you want us to rationalize it?
You do not have to rationalize. Yeah. I don't want to go too far off on a tangent, but I'll just mention, I know students who've had me before know this. A lot of y'all are taught that you're not allowed to leave something like that, right? Like you never leave a root in the denominator, always, it's not, somehow it's not right. But it's okay to do that, because rationalizing, what would you do to rationalize? Multiply top and bottom by root 2? You wind up getting this, right? These two things are exactly the same thing. If you get on your calculator and do 1 divided by that, and you do root 2 divided by 2, you're going to get the same exact answer, right? So why are you told you have to write it like this? It looks prettier. It actually it has to do with before humans had calculators, all right? When we used to have to do this all by hand, right? Imagine if you had to do that by hand, okay, without a calculator. What you would have to do is this. You'd have to go back to old school division. You'd have to take the numerator, put it in a division box, and on the outside you'd have to put root 2, which you would have to know what it is, because you couldn't get a calculator to figure it out. So you go to a book or you would have it memorized, right? There were certain numbers you would just know. This is back before calculators. So you would have to know that root 2 is 1.414, something like that. So think about what it would take to do this, okay? You have to ask yourself, how many times does 1.414 go into 1? I don't know. So you put a decimal, you put a 0, now you say, how many times does 1.414 go into 10? Okay, now, if you rationalize it, how does the problem change? Now, what's in the division box? 1.414. What's outside the division box? 2. Much easier to do. Because 2 doesn't go into 1, right? So I have a decimal, I bring my decimal up. 2 goes into 14, how many times? 7, blah, 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 0, 7. It's much easier to calculate this by hand. Do you see that? That's why you're taught to rationalize, and that's it. Well, that's why you're told rationalize, 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 because it's just some thing that's just followed us. Like it's been taught, pushed, but people don't even ask why anymore. They're just like, you can't leave a root in a denominator. Does that make sense? Like, you don't need to. We have calculators now. So this isn't hard for us to calculate, right? So it's kind of an obsolete idea. All right. One more problem, and then we'll be ready to start partial fraction decomposition. And this problem is just weird, all right? It's just weird. And I'll tell you right now, there's like probably 3 or 4 different ways to do this problem, all right? Are y'all ready? No? What we see here is a linear expression on top, right? X plus 1, divided by x squared plus 1, right? X squared plus 1, y'all agree that's a quadratic? Is x squared plus 1 factorable? Can you factor x squared plus 1? No. You can factor x squared minus 1, but not plus 1, right? So this is irreducible, right? And it's repeated, meaning that it's squared, right? So that's what I'm saying there. You have a linear expression on top, and you have a repeated, irreducible quadratic. What? That doesn't say quadratic. Quadratic. A repeated, irreducible quadratic on the bottom. I'm going to ask you, anybody have any instinct, intuition as to what you want to do? You what? Yeah. In the last one, we had linear over irreducible quadratic, right? But it wasn't repeated. Do you all agree? Pardon me? Oh, expand it all out, like multiply it all out? Okay, we could try that. If we did that, let's see what we would get. This is just, we're trying to take a stab at it, right? So if we take that and square it, you get x to the 4th plus 2x squared plus 1 dx. Y'all agree? Now, what you're actually looking at is where we're headed. This is actually where we're headed. So like, when we get to partial fraction decomposition, we're going to start with this, and we're going to factor it, and we're going to get it to here. And then we're going to be able to do it. So good, at least you're seeing now, how do you handle this? Do y'all see that I cannot use that same idea that I just used, where I said, let's let u be the bottom. Because the bottom is not quadratic anymore. What is it? 4th degree, right? So if I let the bottom be u, the derivative will be what degree? 3rd degree polynomial, right? And my numerator is linear. So there's no way I'm going to be able to like massage the numerator into looking like the derivative of the denominator. It's impossible to do. Do y'all see that? So, I mean, yes, that algebraically we can do that, but it's not going to help us. So let's maybe try what we just did in the previous problem. What did we do? We said, let's let u be this quadratic, right? The derivative of that would be linear, and it's up there, and maybe we can massage it, make it look like that, right? Maybe, I don't know, just try it. So u is equal to x squared plus 1. The derivative of that is 2x dx, right? Is your numerator 2x dx? No, it's x plus 1 dx, isn't it? So what I'm going to do is I'm going to make this numerator look like this. Okay? So I need a 2, don't I? So on the outside I put what? 2 over 2. Remember, my goal of this is to try and get this to appear in the numerator. I pass the 2 through, right? So when you pass 2 through, it has to go to both of those. I'll still have a 1/2 out here. I'll have 2x plus 2, and then over x squared plus 1, that quantity squared dx. Now, is my numerator 2x dx? Not yet, right? In the previous one, I needed to insert, if you look at your notes, I had to insert a -4 plus 4, didn't I? To make it match. Here, it's just 2x, so I don't need to insert anything, do I? I just need to split the 2 in 2 pieces, right? I'm going to split that integral right now into 2. So I'm going to go 1/2 integral 2x over, what, x squared plus 1 squared dx, that's the first integral, plus 1/2 integral 2 over x squared plus 1 squared dx. That's just me taking it apart into 2 different integrals, right? This one should be good, shouldn't it? Because if I make this substitution right here, I replace x squared plus 1, right? Replace that with u, then the bottom is u squared, and the top is du exactly, isn't it? So this first integral becomes 1/2 integral 1 over u squared du. And can you find the antiderivative of 1 over u squared? Don't say natural log, please, don't say natural log. It's not, right? If it was just 1 over u, it would be natural log, the antiderivative. But it's 1 over u squared, so that's u to the -2, and you have to use the power rule, right? Why do you think I'm mentioning that? Because that's one of the big mistakes I see. Students will get to this and they'll say this is somehow natural log or something like that. It's only if it's 1 over u that it's natural log, right? This is really u to the -2, and now you use your power rule, which says you add 1 to that power, and out front you have to do 1 over that. So let's continue this. This would be 1/2 comes down. The antiderivative of that is 1 over -1 u to the -1. That's your power rule. Can I continue that here? 1/2. Isn't that just -1? Out front, right? This is just negative. So can I just put -1/2? -1/2. And then u, what was u? X squared plus 1 to the -1, right? Just drop it down, right?